Good afternoon. Can you hear me? Can you hear me without the microphone? Yes. Okay, in the front row, I believe that. How is it in the back? Okay, good. I try to shout. Probably after 2 hours, my voice will wear out, and then if I speak too slowly, no, that will not happen. If I speak too not loudly, let me know. So, again, I think looking out of the window, this is a beautiful place, and I hope you all, or many of you, enjoyed the view from up the mountain skiing. This is, in some sense, a preview about the things I will discuss probably tomorrow and the day after tomorrow. You see that line transfer, or the transfer of light also in the continuum, is a tricky issue. You have here haze, you have clouds of obscuration, and we will discuss that tomorrow. Today, we will continue a bit on the phenomenology of the interstellar medium. Because after all, I think you need to know, at least in physics and in particular in astrophysics, what is the thing you're dealing with? What are its physical characteristics? How does it look like, quote unquote, before you can, I think, successfully build a theoretical model? So let us, can you read that? Or is it, maybe we try to do something here. No, then you fall asleep. We shall see. So I will give you a very, 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 very short and brief inventory of a galactic disk. And as you will see also, I guess, in Nick's talks later, most of the disk of the Milky Way, so I focus on very local scales, is composed of stars. This is not of interest to us. So what is of interest is this part here. So at the moment, the gas makes up roughly 15% of the mass in the disk. But in addition to the gas, you have dust, which is about 1% in mass. And we shall see this is important when we do the energy budget of the radiation in the interstellar medium. There is also something that is usually neglected by people, including me, cosmic rays. And it is frightening that the energy density in cosmic rays is comparable to all the other energy densities. And typically, we neglect it in our star formation and ISM models. So this is, again, some caveat you would like to keep in mind. Magnetic fields have been discussed in the past, and again, they carry quite a large fraction of the total energy density, of the total energy budget in the interstellar medium. So how do we learn things about the interstellar medium? So we are astronomers, so we look at the sky and do photon counting, which is to be taken literal if you go to X-rays or gamma rays. But you have many photons if you do radio astronomy and optical. And this entire wavelength spectrum gives you information about quite different number of astrophysical objects. Maybe we can remove that a bit. So, in the radio, this is our main source of information about the interstellar gas, radio and submillimeter, because this is where the temperature, the dust continuum sits and the line emission sits. In the infrared and optical, we pick up stars. We pick up the energetic parts of the stars, so the hot coronae or supernova remnants. If you go to X-rays and gamma rays, we see really very energetic events. And this is just such a beautiful picture. I always need to show that when I talk about the ISM, because it really tells you what you see if you look onto the sky and you scan the plane of the Milky Way at different wavelengths. It goes from radio continuum to the atomic hydrogen, again radio continuum at slightly smaller wavelengths. This is the molecular hydrogen, and as we have discussed yesterday and we'll discuss tomorrow and in 2 days, molecular hydrogen you do not see, so you look at the tracer molecule, it is the J1 to 0 transition of carbon monoxide. So very thin disk, very well visible. In the infrared, you start to pick up starlight and near infrared, and in the optical, again, starlight, but you see that there are these dust clouds that block the light of stuff that sits further behind. In X-rays, you pick up individual stars, but also supernova remnants, and you get a very different picture. So how does, if we take one pixel in this image and then scan to frequency space, how does the interstellar radiation field look like? And I have brought you two examples from the book by Bruce Strain. Again, in the break, I have brought it. You can have a look at it. And you see it covers a whole range, or a very wide range of wavelengths. This is the energy density. This is the wavelength. And you can roughly distinguish three peaks. This peak here is the cosmic microwave background. And you should notice here that it carries quite some energy density. So this is the emission from dust, in thermal emission from dust, and here you pick up starlight. And clearly, if you are away from a massive star, this is what you would see. If you go to a massive star, notice this is 10 to the minus 12, this is 10 to the minus 12. You're dominated by the hot emission from dust, heated by the nearby massive star, and you have a large contribution from starlight that goes to very high frequencies. So the interstellar radiation field changes in intensity and frequency distribution quite a lot depending on where you look at. And of course, this can drive different chemical reactions. If you're close to a massive star, you probably are ionized. We've seen pictures yesterday, and if you're, say, away from a massive star, you have mostly neutron medium, or depending on how dense you are, molecular medium. I should also mention that what you can do is you can look at the average intensity, and this has been pioneered by Harm Harbing, and hence it's called the Harbing field. This is a unit of 1.2, 10 to the minus 4 ergs per square centimeter. So you put a little beam into, or a little detector in your beam, and you're measuring basically the energy per frequency band and per steradian. And it turns out, if you go back and you integrate over that the typical radiation field is 1.7 in these Harbing units, and it's usually called G naught. Again, this is an important quantity if you want to couple the chemistry, if you want to do astrochemistry, and if you want to couple that to the ambient radiation field. Typically what you do is, if you are in the vicinity of a massive star, you beef that up. Let's say if you do calculations close to the galactic center, I will show you some results on Friday, then you beef that up. If you go to other environments, you scale that up and down. Good. So how do we categorize the interstellar medium? As Nick has pointed out, physicists typically try to find correlations and relations. The astrophysicists, so the astronomers, have this kind of cupboard thinking, and they try to categorize things in terms of certain specifications. And before we do that, let us look at the inventory of the elements that we see in the interstellar medium. And as you can clearly see, it's dominated by the stuff that was also created in the Big Bang, in Big Bang nucleosynthesis. Hydrogen, this is all normalized to 1 million hydrogen atoms. Then for a long time there is nothing. There comes something like 70,000 helium atoms, and again there is 2 orders of magnitude nothing. Then comes carbon and oxygen and a whole bunch of other stuff. And this is the thing that is breeded by nucleosynthesis in stars. So all of that stuff here, the stuff we are made out of, has been produced in stars and is not present if you go to the primordial universe. So if you were to make, let's say, a star formation calculation in the primordial universe, your chemical network you would be invoking to calculate the cooling and heating functions would be very different than at present days. So clearly this one dominates, and we put hence the ISM into three categories depending on how the atomic, oh no, not the atomic, how the depending on the chemical state the hydrogen is in. So it can be ionized. This is then called an H2 region, which comes from the spectroscopic classification, so it's H+ if you're a chemist. It can be neutral. Oh, this is German here, I see. Or it can be molecular hydrogen, again H2, but now the Roman subscript. And it turns out that the transition from one to the other can be extremely sharp. And we will quickly calculate the transition from the ionized to the neutral part later on. And if you look at such a photon-dominated region, a PDR, if you look at side on, you see the transition from being dust enshrouded in molecular to probably ionized here can be very, very sharp. So what you can do, you can basically make first simple models. This is now quite old. I think I took this from a picture that, from a book that Gensel has published 25 years ago. You can take a slab of gas, you put in your favorite chemical network, you shine some radiation, in this case from the left-hand side, in your case into it, and you see how the radiation penetrates inside and influences the chemistry. And here where you have lots of UV radiation, you see the stuff is ionized. You recognize here the ionized hydrogen. You see a transition layer. Here you see another transition layer to the molecular gas. If your chemical network includes carbon monoxide, you see here you have ionized carbon, atomic carbon, and here you are in the molecular regime. And you notice that this has been also scaled to units that the observers are using, to extinction units that are coupled closely to the amount of dust, to the column density of dust you have. So this is a visual extinction of 1, of 10, of 100. And roughly speaking, you can convert that into column densities, 10 to the minus 21, particles per square centimeters, 22, 10 to the 23. So with that knowledge, you can now place, you can make the first simple picture of the interstellar medium. The three-phase medium, or the three-phase picture of the interstellar medium that has been put forward by Chris McKee and others. So you can say, oh, I place now a blob of gas into a sea of UV photons, and you see it is hot and ionized at the outside, and it gets colder and colder and denser, and it transforms from being ionized to neutral to molecular. If you say, I have a hot star inside such a bubble, you just invert the process, and you have something like this here. So what we will discuss now as a start in this lecture and then tomorrow is these phases are closely connected with each other by quite a number of feedback loops. So for instance, if we start with giant molecular cloud complexes, so the very massive, very cold, and very dense molecular phase, this is where stars do form. So there is an error to this place, but stars then make supernova, stars shine, so they influence in a dynamical sense, in a chemical sense, and in a radiative sense, the interstellar medium. It could make very, very hot gas, let's say in the coronae of stars, or in supernova explosions. It can make by ionization H2 regions. It can recombine to the warm neutral medium. It can turn into the cold neutral medium. It can go back and forth. Eventually, as I have tried to indicate, if you just beef up the density, you can go into cooling instability. Little droplets of molecular hydrogen may merge to form larger and larger things. Finally, you have molecular clouds, and they form stars, and you have this very complex pattern of intricately interwoven feedback mechanisms. And again, to understand that is what star formation theory and ISM dynamics needs to or will try to attempt nowadays. Good. let me now go to the different phases we have discussed. Let me start with dust, and let me start again with a very beautiful image of the galactic plane. This is from Paranal, from ESO, and again you see these patches of obscuration that block out the starlight in the background. We can zoom into, this is by the way the Ralf cloud that we have seen yesterday in dust emission, and it looked very, very different. We can zoom into this picture and we see that typically when we have starlight, dust acts as a medium that blocks the starlight. It has a very high absorption capability at optical wavelengths. But this energy it absorbs at optical wavelengths, it gives out at other wavelengths, typically at its thermal wavelengths in terms of thermal emission. So we can also look at the galaxy in emission. This is, for instance, what the Planck mission does. So Planck is, I think, an extremely exciting galactic mission because it helps us to understand dust emission in our galaxy. That it has some side issues and gives us some cosmological information is, to me at least, some second order effect. So we have a fantastic all-sky map of dust emission of the galaxy with superb resolution, with many, many channels. And again, we can classify several issues or several features. We see the galactic disk, we see the large and small Magellanic clouds, we see some of the nearby molecular clouds. Here's Andromeda galaxy, here's Orion, I've shown you yesterday, and here are quite a number of features. Some are clearly extragalactic. And I show you just another example. This is the Ralf cloud. So a fantastic mission. We have also polarization, so we can learn a lot about the large-scale distribution of magnetic fields in the galaxy as well. Now, what is this dust? We have seen that it absorbs typically starlight and radiation at high frequencies, but gives out this energy at low frequencies. So it acts as a thermostat. And dust is typically composed of the dust you also have at home. So if you go to some corner of your room, you slide your finger. This is very similar to the dust you see in the interstellar medium. So on the very smallest scales, it is just an accumulation of polyaromatic carbon cycles, the so-called PAHs. These can accumulate together to larger and larger entities. They can have micrometer size entities like this thing that has been taken from the Stardust mission, where people shot up a satellite into space with some aerogel that tried to catch interstellar, but mostly interplanetary dust, brought it back to Earth, and you can then look at these things in the laboratory. So it ranges from this thing to this thing, and clearly the size and the composition matters in terms of absorption coefficient that we calculate. What is important to notice is at no means this dust is spherical. It has a very high surface to volume ratio. Typically it has these fractal, elongated, complex structures, and because dust acts as a catalyst to drive chemistry in the interstellar medium, this is very important. Because, for instance, you form molecular hydrogen by taking a molecule, it absorbs onto the surface of a dust grain. Because it is very loosely bound, it can hop on this surface around. It will find another H atom. They bind together to the H2 molecule. This releases energy, which brings the molecular hydrogen now back into space. So this is how you make molecular hydrogen. So an important catalyst of chemical reactions in our Milky Way. Yes. If you look at dust, it is important to notice that, maybe I go back, that the extinction coefficient is a function of wavelengths. This is inverse wavelengths, so these are higher frequencies, lower frequencies. And extinction grows as you go to smaller and smaller frequencies. You see that if you look at, this is Benar 68, famous globule in the vicinity of Ralf.
And you see that because the background starlight, that this wavelength is longer and longer wavelengths down to see through this cloud. So you can use that to learn something about the column densities. So you can reconstruct column density images from dust extinction mapping. This is an important way of learning something about the distribution of masses that is unbiased from line emission. So this is a very good way of learning something about the mass distribution in nearby clouds. So this is the reconstruction, and this is another caveat. This is the same object now seen in different molecular line tracers. N2H+, a high density tracer, C18O, so carbon monoxide with this particular isotopomer, and CS, which is a shock tracer. And you notice that N2H+, a high density tracer, is mostly seen in the high density parts of the blob of gas of Bernard 68, but you have a hole there in the carbon monoxide. You also see very little carbon monoxide out here. So what we learn from that is that all these tracer molecules have only certain ranges of where there are useful tracers. At low densities, for instance, carbon monoxide is not thermally excited by collisions to emit a line. You need a certain number or frequency of collisions to make radiative transitions. But in the very center, the carbon monoxide dissolves onto the dust grains. So they freeze out onto the surface of grains, make ice mantles, and then they are again out of the dust, out of the gas phase and invisible to us. So that means if we look at the total column density from this thing, from the dust extinction, we learn a lot. But when we want to study chemistry and velocity information, we need to go to these tracers, but we need to keep in mind that they can be very deceiving. If we had only this information and would not know about the chemistry of carbon monoxide, we would get a very different impression of this cloud core than what it looks in reality. So dust is useful also here to give us an indication of the density structure of things. If you remember the shape of the dust grain I've shown you before, it was not spherical. It was elongated, and it is typically has some charges. So if you have something that is elongated and has a certain charge, it typically adjusts itself to magnetic fields that may thread through your volume. So if you have an elongated dust grain, it starts to spin around magnetic field lines. And because when it spins, it acts like a dipole. We know dipole radiation is intrinsically polarized. This gives us a reason why the dust emission must have some degree of polarization, both in extinction but also in emission. So the way it works is we have magnetic fields. The dust grains are charged. They are elongated, so they align in a specific direction with respect to the field lines. They are no longer statistically distributed. And because they emit mostly via dipole radiation, we have a certain degree of polarization. And we can use that to learn something about the degree of polarization in the galactic plane. And we see it can have very complex patterns. And if you compare this image with the Planck image, which has polarization basically everywhere, you see that this is a big advantage. But this is from a specific molecular cloud core, the Orion molecular cloud core 1 and 3. And again, you can see that you can use dust polarization to learn something about the morphology of the magnetic field. So you see the field lines have certain structures. And only very rarely are they somewhat random. Often you see some ordered component to it. Good. This is a digression because cosmic rays are usually not treated in great detail. And
for me, or for us, or for those who do chemistry, cosmic rays do exactly two things. They provide some ionization rate, and they provide some heating rate. And because we have very little ideas how cosmic rays penetrate through the galaxy, typically what is done is that people assume there is a constant cosmic ray flux that just goes through a cloud everywhere in a homogeneous fashion. So cosmic rays follow a great power law on the sky, if you wish. This is the energy distribution. It goes from here, 1 giga-electron volt to 10 to the 12 giga-electron volts. And typically cosmic rays are protons, but we also have a few electrons, we have a few positrons, etc. But this is the energy distribution of protons, and there are several features. There is a power law here, there is some knee or bend in the slope, and there is another power law, and there is a truncation at the most energetic particles. So how do you produce the cosmic rays? How can you accelerate particles to these enormous energies? If you take a proton at these energies, it has the same kinetic energy as a, how do you call it, tennis ball when you play tennis. And that is enormous for such a tiny particle. So cosmic rays are produced typically in the expanding shells of supernovae and other objects that drive interstellar turbulence. The way it works is they can be reflected by fluctuations in the magnetic field lines. Yes? So say you have a supernova shell that expands, and it has a very fluctuating magnetic field structure in it. The idea is that you have a cosmic ray that comes in, somehow it scatters at the field lines, and it goes out again. But if the expanding supernova shell goes in this direction, and the cosmic ray enters with an energy 1, it exits again with an energy E2 that has the original energy, but also gains some energy because it has been accelerated by the expanding supernova shell. And if it goes back and forth many, many times, you can step by step and gradually gain lots of energy. So this is the Fermi process, Fermi 1 and 2 in a nutshell, that can accelerate charged particles in the interstellar medium and beef it up to very, very high densities. So how can you make this reflection? There are basically two ways. A, it can gyrate along field lines that simply bend out again, or it can gyrate along field lines that are converging together. So it would gyrate like that, but then it would be reflected back by the fact that the field lines getting closer together. How do we detect these cosmic rays? We typically detect them by making particle showers in the upper atmosphere. Say there comes our highly energetic proton. It hits another proton or molecule or whatever in the upper atmosphere. It creates pions and other things like hell. They make a whole cascade of highly energetic particles. Some of them go faster than the local speed of light in this medium, and you observe Cherenkov radiation in detectors like these. This is the Hess telescope in Namibia. And you can then get an idea about the direction and the energy of these particles. Good. That was dust, that was cosmic rays. Now let us come to the three different gas phases that we have in the interstellar medium. Let me start with the most energetic one, and let me start again with a beautiful image. So this is the Trifid Nebula. Again, you have a huge ionized cavity. You have some dust that has survived it. Same here. You have seen that before. A huge ionized cavity created by Trumpler 14. And we have also discussed the Orion Nebula cluster, the Orion Nebula. So this
large H2 region that is driven by theta 1c Orionis. So what happens here? What happens here is very similar to what Nick has told us earlier today about the reionization or ionization of the universe. Let us assume we have a homogeneous cloud that is composed of hydrogen atoms. And inside this cloud, we place a star, a massive star, that emits a certain amount of UV photons that can break apart, that can ionize the molecular hydrogen. So we have seen that you need at least 13.6 electron volts to basically take the electron from the ground level and detach it from the proton. Then you have a plasma, you have the free electrons and the free protons. And we can make an equation of detailed balance. You have then the proton and the electron, and they are in balance between the hydrogen and the photon that comes along. And this forward or backward rate, so the recombination rate in equilibrium, must be equal to the ionization rate. So we shall see that in equilibrium, all the forward reactions must balance all the backward reactions. That is a principle that helps us a lot to understand chemical reactions, like this one. So this is the conditions that we have in these ionized regions. So what we need to do now is we need to ask ourselves, what is now the number of recombinations I have, and what is the number of ionizations I have? And when or over which volume do these two rates balance each other? A quick question. This is relatively small font. Can you read it in the back? No. Not really. Okay, then I try to make it larger. There are only 2 slides of that type today, but also I noticed when I was sitting in the back that this is difficult to read, right? Okay, I try then in the future keep these empty. I'm not sure I manage. So the idea is again to look at this detailed balance, and what we need to know is the recombination rate. So the recombination, or the number of recombination events, depends on the volume. We assume a spherical volume. It depends on the recombination rate, some 1/2 thing, and it depends on the number density of the protons and the electrons. This is important. Recombinations always depend on the density quadratic because you need the proton and the electron, you need to bring them together. So these cooling rates are quadratic in the density, and if you say the number of ionizing photon that is emitted from the star is simply Q naught, then you have an equation that you can solve for the radius. The radius then depends simply on the flux or the number of the photons divided by 4 pi alpha number density of the protons, number density of the electrons, and you take the 3rd square root. So this is relatively simple. This is what Strömgren did quite some while ago. And you see it creates a spherical bubble of ionized gas. We can ask, well, how quickly is that established? And as you can guess, photons travel relatively fast with the speed of light. We can calculate how quickly this Strömgren sphere is fully ionized or is ionized. There are always some recombinations, so the ionization degree is not 100%. So the ionization rate we can also take from the previous example. We take simply 4 pi 3, the volume of the Strömgren rate, times the number of the hydrogen atoms. I divide by the number of ionizations. This gives me this rate. And if I plug in the numbers, this is something like 1,000 years for densities of only 100 particles per cubic centimeter. So typical molecular cloud densities. So if we switch off the star suddenly, how quickly would it recombine? It is again the same rate, 1 over the density times the recombination rate. So again of order of 1,000 years.
So this thing within 1,000 years is fully ionized, but then suddenly it finds itself overpressured, because now you have created gas that has maybe 10,000, maybe 20,000 Kelvin, and it sits in an environment that has maybe temperatures of only a few tenths Kelvin. So there's a huge pressure imbalance, the region starts to expand. And we can calculate the expansion timescale by looking at the sound crossing time through this Strömgren sphere. So the speed of sound at 10,000 Kelvin is something like 13 kilometers per second. And it turns out that this is wrong. So it turns out that the Strömgren sphere then expands typically on timescales of, say, 100,000 years. So instantaneously it is ionized, as we have heard this morning, and then it starts to expand into the ambient medium on timescales that is more of the order of 10 to the 5 years. Good. Let me go now to the atomic gas, and please interrupt me if you have questions, right? This is not, I'm standing here, this should be interactive. So how do we see atomic gas? There is the famous 21 centimeter line. Basically what can happen is that the proton and the electron that cruises around the proton can have parallel spins or antiparallel spins. And it turns out that the antiparallel state is slightly energetically favorable, and the energy difference corresponds to 0.07 Kelvin. If you convert that into a frequency or a wavelength, this is the famous 21 centimeter wavelength. We can compare the timescales, so it is collisionally excited, typically of order of 1,000 years, say, and it is radiatively de-excited on order of millions of years, 10 to the 7 years, say. So the radiative de-excitation is compared to the collisional de-excitation very rare. So typically what happens is you have a very optically thin radiation. So if you look at the 21 centimeter, you can see through the entire galaxy. And if you do that, you see again a structure that looks very similar of what we have seen before. You see the galactic plane and you see certain structures. You can correct for certain features, and you see again the galactic disk. You see these huge flares that are probably foreground stuff. We can also use that for extragalactic observations, and we see that the galactic or the gas extends over much, much wider radii than the stars. So this is the stellar light distribution of a tidally interacting group in M81. And you see that if you look at the H1, the 21 centimeter emission, you see that these four little things are connected by large tidal streams. And this one is not visible at all in optical wavelengths. This is just a starless H1 blob of gas. So this is an important tool of learning about the gas dynamics on galactic scales. Good. Finally, this inventory let us go to molecular clouds, and I will discuss these transitions in more detail than tomorrow. Typically what you have is you need to look at tracer molecules because the main constituents, the H2 molecule, is symmetric and does not emit very strongly. So if you then have a very simple diatomic polar molecule, let's say carbon monoxide, the two most abundant other elements after hydrogen and helium, typically when you have them, they find each other, so they make the carbon monoxide molecule. And there are now three things that can happen. The electrons that bind this stuff together can go to higher
electronic transitions. The thing as a whole can vibrate, so the carbon and the oxygen can vibrate through with respect to each other, or they can go into rotation. And as we can expect, the electronic transitions are energetically very strong, or need lots of energy to be excited, typically of order of the binding energy, so we talk about electron volts. Vibrational transitions are typically in the energy range of 1/10 to 100th of electron volts. And the rotational transitions are very easily excited. They are typically on 1,000th of an electron volt. This is just a sample of typical molecules we observe in the interstellar medium. I skipped that because I will say more about the vibrational and rotational spectroscopy. The only thing I would like to say now is that besides carbon monoxide, there are many, many molecules now discovered in space, and they can give rise to extremely complex spectra. So this is already quite an old spectra that has been taken of one of the hot cores, maybe Orion Molecular Core 1, OMC1, in the Orion constellation. And you see there are many, many, many lines. And you should notice that there's quite a number of lines that simply have not been identified. The rotational and vibrational spectra can be so rich that if you have more complex molecules, these lines are simply not known. So laboratory work is needed to identify these lines, to make models of where you would expect lines for certain more complex molecules. And I'm providing here a link to the wiki page, list of interstellar and circumstellar molecules, because I think that is very useful and tells you about the latest status of the different molecules that are discovered and identified, and you can look them up. You can click on the molecules and you get some information. Good. Why is this extremely useful? Unlike the dust emission that gives us either in emission continuum or in absorption only information about the column densities, because we have lines, when we have identified them, we know exactly at what frequency the line should be emitted in the rest frame of the molecule. If we observe it at a different velocity with respect to us, we see that the emitter has been moved or has been in motion with respect to us, and we see the line Doppler shifted. So typically what people do, they take like the CESS telescope, they scan, this is the Orion A cloud, at different positions, and they collect the spectrum they see in these positions. This is an example. Here is a position, and velocity are these little pins. You see lines in each of these little pixels. So you can use that, these position velocity cubes, to learn something about the velocity structure of these clouds. And I show you a little movie on the result of such an analysis later on. The molecular gas, we typically distinguish between different components. So there are the diffuse molecular clouds, the cirrus clouds, that are not actively forming stars. The Polaris flare is one of those. They are typically slightly above or below the galactic plane. Then there are dark globules, very small, very dense, very cold features. You have seen Bernard 68. Typical radii are of order of 0.1 parsec, then they would form only 1 or 2 stars. If there are something like 5 parsec, they are called infrared dark clouds, and they are probably cluster-forming objects. On the other hand, there are the giant molecular clouds, which can have radii between 10 and 100, and masses like 1,000 to 1,000,000 solar masses. And we have seen that the velocity dispersions can vary wildly from almost thermal to something that is very, very large. And this is the velocity gradient. So the actual velocity is not given here.
And like in this molecular cloud course where you already have an embedded high mass star, the temperatures can be very high and you can drive lots of interesting chemistry. So I skip that, and I would like to go through the CFA survey of the galactic plane of the CO molecule. And it has 4 quadrants. I show you the quadrants because I think it is illuminating to compare the molecular gas emission with the optical image. So in this optical image, you see the plane of the Milky Way. However, you also see these patches of obscuration. And we can now overlay these two. No, what happened here? This. And we notice that if you blink, we see a very close correlation between the dust and the molecular gas. And the same here, where the galactic center is on the right-hand side. Again, we see a close correlation. 3rd quadrant, same thing. So what we learn from that is that dust is closely correlated to the molecular gas. So not only can we use these tracer molecules as traces of the cold molecular gas, also dust opens up this possibility. I have mentioned it in the passing before, but this is another visual impression or illustration that this works typically very well. Good. I have shown you these images, I skipped it. So the molecular clouds are the high density regions in the interstellar medium. Because they are high density, they can shield themselves from the ambient radiation field, and hence they can keep the molecular hydrogen and other molecules alive. So they are shielded from the harsh radiation field and they can stick together. Because they're well shielded, many heating mechanisms fail. Only cosmic rays can penetrate into these clouds, and hence they're very cold. We've seen they have very complex velocity and density structure, and we see that at present days at least all stars form within the molecular clouds. And whether this is a causal connection or just happens that molecular clouds form along the star formation is a different issue. I want to end this inventory by showing you that most of the nearby molecular clouds that you see in the literature, so you see Monoceros, MonR2, the OB association in Monoceros, Chameleon, Coalsack, etc., all these Orion AB cloud, Taurus, all these fall into one structure that is called Gould's belt. So all of these are relatively nearby. They have distances of up to, let's say, half a kiloparsec. And if you trace them on the sky, they seem to follow this ring that is slightly tilted with respect to the galactic plane. And we are more or less inside this ring, and we are looking at this structure. And this structure has been called Gould's belt. This is a 3-dimensional image. The sun is somewhere a bit off the center. And if you look around, you see all these huge star-forming regions, nearby star-forming regions associated with it. So what might have caused that, one of the ideas is that maybe there was some satellite galaxy that was plunging through the halo, not through the halo, through the disk. And like if you throw a stone into water, it makes these ring-like perturbations. It has basically created this ring of high-density gas, the shock front that was sweeping through the disk and collecting material that then has fragmented into these dense clouds. Because it is tilted by something like 10 to 15 degrees, this could be an idea. But maybe it's just a fluke. So again, this is one of the debates that are in the community. What is also interesting and what is not so well known is that the sun is embedded into a very local bubble. So there is lots of hot gas in the vicinity of the sun. So the sun is not in a very typical environment in the galaxy, but in this hot bubble. And this was probably created by a supernova explosion that was going off in the vicinity of the sun, not that long ago, maybe 30 million years or so. And some people claim they see traces of that by looking at iron layers in some drilling holes in the Atlantic sediments. So there are then interesting connection between the intermediate or immediate environment of the sun in the galaxy and indeed terrestrial features. Good. So this little inventory has taken a bit longer than expected. Now what needs to be done? I have tried to argue now several times that the interstellar gas is highly turbulent, because this is a school on numerical and theoretical concepts. I would like to spend now the next hour on discussing certain properties of the turbulence and how we model this turbulence on a computer. Then I would like to discuss the possible physical mechanisms that can drive this observed turbulence on galactic scales. And then I want tomorrow, and the day after tomorrow, discuss a bit how to implement chemistry and chemical processes into our hydrodynamical models. So I think this is a good time to make a short break. How long should we break? 5 minutes?
Let's wait for 5, yes.
Okay, so then we continue at 6.